Oh, joy. Okay, so no
Posterity.
say anything
Posterity.
bad. Gotcha.
All right, so go ahead. The floor is
Okay.
yours, Vivian.
Um, right. So basically, let's see. I'm just gonna talk a little bit about robots and give an overview about robots and kind of the state of robotics, and then dive a little bit into what it is that I think are cool about robots and kind of relate that to my work. So yeah, so right now I'm a PhD student at Georgia Tech, hopefully going to graduate very soon. Okie dokie. So, robots. So most people, when they think about robots, it's pretty much what you get from the movies, the TV shows. You have a robot that will be at home and clean and cook for you, and it's cute and adorable and will listen to you and can walk around without falling over and all sorts of things. But in reality, robots aren't like this at all. Traditionally, actually, robots have been very successful in settings more like manufacturing, so the top view images, where you have, this is a KUKA robot on the top right, where essentially it's a robot arm. It only really knows where it's supposed to go at any point in time, and it'll execute that motion very accurately time and time again. And then you essentially get these things on the left where you have these robots, they're put on factory floors, and they build cars again and again. It's not very safe because they can't actually sense anything around you, so you never want to walk on a floor where there's these robot arms moving. And then another area of robotics that has been really successful in the past few decades has been in space. So you could have examples of Curiosity and the rovers that go through space. These robots actually do have to have a little bit more intelligence built into them. So that means they actually have to plan and navigate. And because there's such a delay to send a signal from here to Mars, it means you can't just drive the robot around. You have to actually say, okay, I want you to go to this spot, but how you get to that spot is how the robot determines that on its own. And so those have been the robots that have traditionally been very successful in the past 30, 40 years. But more recently, hopefully people have been seeing the news, robots that have been a lot more social and a lot more friendly and can be deployed in environments where there are people around. So you have robots such as on the bottom left, the Jibo, and this one is the Curry from Mayfield. And these are robots that actually are intended to be put in people's homes. They're supposed to interact with you, they're smarter. And the reason why this has started to happen in this past like 5 to 10 years even is because hardware in general has just gotten cheaper. So things like these robots on the top, these are hundreds of thousands, if not millions of dollars when it comes to building these kind of robots. But these robots on the bottom start to become in the hundreds. And the reason is because things like sensors, your cell phones, cameras, accelerometers, all these things, because they become mass production, that's something you can afford now and become hundreds of dollars instead of hundreds of thousands. And so this gives rise to computers that are smarter and smaller, and they can fit in these small sort of form factors, which means robots can start to be useful. With that said, robots are still really dumb today, and I'll give you some of these more recent videos, some of the state-of-the-art things that are happening with robots. So yeah, so before I get into some cool robot videos, I kind of want to just talk about robotics and what does it mean to be studying robotics and doing robotics. So robotics actually encompasses a lot of different disciplines. You have your traditional disciplines like mechanical engineering, electrical engineering, which build essentially the muscles and the control and the power of motion. You have also aerospace engineering that does a lot of the dynamics and controls and planning of how you actually get from point A to point B. Then you have some of these newer fields like computer science and cognitive science and psychology that really want to try to actually give the robot actual brains, AI essentially, artificial intelligence, and really trying to study how we as people function and think and be able to process the world, and how can we translate those into computational models that the robot can then understand and use as well. And then one of the other fields is also biomedical engineering, which has actually a lot of success with robots. One of the most successful robots is the Da Vinci robot, which is a surgical robot, where a surgeon could sit down at this robot console and essentially be controlling this robot at a console where remotely at a location a little bit further away, the robot's actually in the patient and doing the surgery. And this does things where, because the robot can be much smaller than a person's hand, then you don't have to cut up the person completely now to perform surgery. You can now have these small incisions, and that means people, when they go in and out of surgery, it's a lot faster, the recovery time is a lot faster, and in general, it's just a lot less trauma that happens. And so at this point, there's been thousands and thousands of these robotic surgeries that have already happened. So yeah, so this is just a smattering. There's, I'm sure, fields that I haven't remembered to talk about in robotics that are also included. For me, my research kind of falls along this discipline side. I'm really interested in how we can program robots to be intelligent, so the artificial intelligence within the robots. And this really is a combination of the mechanical engineering side, where you understand how motion and kinematics and transforms actually go from one point to another, and then connect that to psychology and human factors. We say, how do people understand? How do we develop and when we learn about the world? And then now how do we translate into those computational models that are essentially all about the mathematics and statistics behind modeling the world and the environment and giving that to a robot. Okay, that's a lot of information, so let's have some cool videos in the meantime to break it up. So this is actually a really recent video, this next two, from a company called Boston Dynamics. They probably released this earlier this week, and so this kind of shows you the state of the art of what we can do with robots. So this is what they call their Spot Mini. It's supposed to be like a robot dog. Hopefully you guys can see it. So I think the company is trying to make the robot cute and adorable, but I think it's very creepy. But you can see that the control.
Creepy.
I agree.
The robots are usually really creepy looking.
Yep, Boston Dynamics.
I like it. I want one.
You want one? Yeah, no, I mean, there's a lot of people. It's like it's definitely a very, it's amazing in terms of what it can do. And I'll show you another video that they just released in terms of how amazing they can get the robots to do stuff. And then I'll show you in reality how robots probably can't do that all that well all the time, and they're mostly there to do it for videos. So here's also a really, really cool new improved robot video.
I saw that in my Facebook feed this past week.
Robot parkour.
Vivian,
Yep.
For the rest of the presentation, if you could slow down a little bit.
Oh, okay.
For our non-native speakers, especially when you talk about the technical parts.
Sure. Yep.
Thanks.
I definitely speak quickly in general, so being told that is helpful. So the robot is doing some pretty crazy aerobatics here, but what they're not showing, and they actually do show a few bloopers, is that the number of times the robot has probably had to do this is within the hundreds of thousands to get this one video that the robot can then successfully do it. Okay, so just to bash that in, as well as show what robots really actually in terms of the capability can do before I show my videos, to set expectations. So this is a video from the DARPA Robotics Challenge. So DARPA is this government agency that funds a lot of the research that happens in the US. And so they have these grand challenges. So in the past 10 years, one of the grand challenges was self-driving cars. More recently, the DARPA Robotics Challenge is all about how to get humanoid robots into disaster environments. So the motivation was Fukushima and how we couldn't get people in to turn off critical valves and do the things that needed to happen. So they said, okay, can we get robots to be humanoid with arms and legs to crawl through the rubble, to turn pipes, to turn things on and off? And so this was the finals, I think a year ago or 2 years ago. So state of the art, all the top universities competing with these robots to try to get them to do things that are just as simple as walking upstairs, just walking on sand, turning valves. And this is just a compilation of those robots not succeeding majority of the time. So walking is actually really difficult for robots to balance. There's actually, I don't remember the exact number, between 30 and 40 different actuators these robots have to be able to balance. And for full body motion, it's almost 120 different actuators that have to work together to make sure you don't fall over. And the interesting thing about this challenge was that this actually has not very much intelligence built in. These robots are all controlled remotely through several monitors, many different people, all with different types of joysticks and controls to try to get the robot to do these kind of things. And they're still struggling to just do the basics.
Wow.
So yeah, if you look up robot failures or DARPA Robotics Challenge failures, you can see a lot more, as well as some interesting soundtracks that go with them. Okay.
Vivian, speak more slowly.
Trying. Okay. Let's see. So I'm gonna pause this really quick. So in terms of my own robotics projects, I guess I'm now gonna kind of go through some of the things I've done. And how they kind of relate to where I am now. So this was a project that I did in college. In particular, we were trying to understand how to get a helicopter to fly on its own. So for those who are unaware, helicopters are really, really difficult to fly. In general, real helicopters obviously are very hard, but even just these miniature 6 degree of freedom helicopters actually takes many, many hours to learn how to do. And so this is a video of us trying to fly one of these. And it's just attached to a stand. Let me see if I can turn off the volume. So it's attached to the stand so it doesn't fall over, and it's just one of my teammates trying to fly it, and we're struggling to get it to even get off the stand. So what we did for our project was we took an accelerometer, so these are the sensors that are in your phone, that tell you essentially where your phone is facing at any point in time, and plug that onto a circuit board and attach that to the helicopter. And so by doing that, we essentially connect what the robot thinks it is doing to the motors so that we tell the robot, okay, make sure you're always in this state and make those motors do what they need to do to be in that state. And we essentially use PID controllers that do this, which is a very classic type of control structure that is done in aerospace and as well as electrical engineering. So video.
You look like a boss.
This was such a long time ago.
Much faster, that it just comes off the stand. We later pan back to show my teammate, he's not touching the controls, he's just letting it go. So it basically, the robot, the helicopter in this case, is hovering and balancing without us having to do anything by using these control signals. And in fact, are better at it than we are. Okay, I'm gonna I realize I turned off my sound, in which case I can't hear what you guys say. So this is another project I had in my master's program. And the class basically, as the final project, wanted us to play robot hockey against each other. So that meant that every team got to build their own robot, 3 robots, and then the robots had to play against each other hockey. And so here's a video of just getting the robot to try to find the puck. So in this case, some of the technologies that we use.
That's a good shot.
I really wish I knew how to turn off the sound on these videos. Anyways, the puck itself has IRs light that is emitted. So this is sort of the light that you have in your remote controls when you point at your TV. And so the controls for the TV, so then the IR light that comes from that is essentially what this puck is emitting. And so the robot is looking for this light and essentially going from there and finding it. I see chat.
And just to be clear, IR is infrared.
Oh,
Vivian,
yes.
Don't use acronyms. Speak more slowly.
Gotcha. Actually, I didn't remember what IR stood for thank you. Okay, so that's Robaki. So yeah, so those are some, I guess, hopefully interesting robot videos that can essentially give you a sense of what we mean by robots and what we mean by sensors and actuation and movement. I'm gonna now kind of walk through my own research and how they relate to my what I'm really interested in and trying to get robots to do. So specifically, I mentioned before, there's a lot of robots in factory floors, and that's actually where the majority of robots are today. And these are robots that, if you can see, there's like barriers along the side that prevent people from walking near the robots. And they are essentially behind cages because they don't sense the world. They can't tell if a person is walking, and if you get in the way, you will get hit by these robots. And so what I want to be able to do in my personal research, and a lot of research that's being studied right now in robotics, is how to go from this environment to something like this really messy room. How can a robot that doesn't sense anything have to now sense this, be able to tell that it's messy, that things in the way so it doesn't trip, not destroy my monitors on the left when it swings about? And how can it actually do this? And in particular, my research really focuses on how robots can use the different sensor inputs that we as people have, that robots actually don't use. So state-of-the-art robots focus entirely on using visual inputs. So a lot of them just have cameras attached to what they're seeing, and that's all they really use. And so what we use as people, like for instance, if we take this lamp, if I want to turn this lamp on, I use my visual feedback to find the chain. I use touch sensing to be able to grasp the chain. I also use force to figure out how much to pull so it doesn't tip over. Then when it actually turns on, I hear a click, so I hear the audio feedback. And then hopefully the light will turn on so you have that visual feedback. So this whole integration of sensor modalities is what really allows us to be more robust to different changes in the environment. So for instance, if I'm trying to turn on this lamp, and I feel the click and I hear the click, but no light comes on, I can start to do things like, oh, maybe the light bulb has gone out. And this kind of intelligence doesn't exist in robots today, and that's what my thesis has really been focused on. And so the question really comes, how do you get a robot to learn about these different modalities? And in particular, the challenge of this is that for the robot to learn about these sensory inputs, like touch, like what does it feel like to turn on the lamp? It physically has to go turn on the lamp. So how do we get a robot to do that? So this is where, so this is the robot that I use in my lab. It's, we named the robot Curie. Curie has a lot of different sensors and actuators. So it has a 7 degree of freedom arm. So a degree of freedom is essentially a degree that you can move. So it has 7 different motors in the arms. And so that allows it to essentially move through space in a very wide range of possibilities. Because space, like to represent a point in space, you need 6 degrees of freedom. And so if you have 7 different joints, then you can reach all different degrees of freedom. We have inside the wrist of the robot hand, it has what we call a force torque sensor. So what that means is that it can actually feel when it's hit the table, it can feel how much pressure it puts when it's interacting with different objects. Mounted above, as well as in its chest and well as its eyes, we have cameras. So the interesting thing about these cameras is that you notice that I say it's an RGB-D camera. So this D means depth. And it means that this camera can now tell the robot how far away things are in space, which is actually very difficult to do. And this camera is essentially identical to the one you get with your Xbox. So your Xbox Connect is this camera. And so prior to people having the Xbox Connect, they had to spend maybe $10,000, $20,000 to build the camera of that kind of setup, as well as probably spend an entire like PhD thesis to get this to work. Whereas now you can just go pay $100-something to get this sensor and put it on your robot. So this really has revolutionized the whole robotics area in the past 10 years. We also have microphones in the chest. So this is how the robot hears things, so that we can capture the audio sounds to be able to learn from. And yeah, so I mentioned how we need to actually have the robot physically interact with the world in order for it to learn about the different senses. So if it wants to understand what it feels like to lift this lid, it has to go lift this lid. But to program a robot to actually get that lid off of a jar is not easy. I would have to sit down on a standard programming interface and maybe spend weeks or months saying, okay, I want the arm to go to this position and then this position, then I want it to close its hands at this exact location. When it feels this much force, then you want to lift. And so this whole process is not easy. So what we do instead is that we kind of take inspiration from how we as humans learn from other people. In particular, when I want to show someone how to do something, or when parents show children how to do something they've never done before, they will physically show the person how to do it. And so we use this and we call it kinesthetic teaching, where we just physically show the robot how to do this. Start here.
Okay.
Go here.
All right.
Close your hand.
Yes.
Go here.
All right.
And here. And so aside from now showing the robot how to go do this, there's a couple of things that you saw in this video that is very important to, in general, social robotic research. You'll notice that we use voice to be able to control the robot. And you notice that the robot actually responded, right? When I said, go here, start here, the robot says, okay. And so this actually gives me feedback while I'm teaching that the robot heard and understood what I was trying to show it. And then you'll notice, hopefully, that the robot was looking at where it was going. And this is also another cue. So when I talk to you and show you how to do something and look at something, if I see you looking at where I'm pointing to, then I understand that you have also understood my feedback. And so these are some of the interesting things of social robotics that are incorporated into these learning systems that really are important to the overall system. Okay, so now that we've physically shown the robot how to do it, then the robot now can just take that exact thing that we showed it and play it back. Okay, so some things you might have noticed in the video, that the robot did fail quite a few times before it actually got the lid off of the jar. And that's actually something that is useful to know. And because there's a person helping the robot along in this exploration, we actually collect both the interesting inputs from failing as well as it getting it correct. And now that actually the robot has learned and can use information about what it shouldn't do. So when it has failed, oh, it feels like this, it looks like this, it sounds like this because I've dropped the lid, as well as comparing it to, okay, this is when I succeeded. I actually feel the weight on my hand, as opposed to not feeling it when I have failed. And so this sort of exploration and guidance process is how we essentially collect this data that the robot uses to then model what it means to succeed and what it means to fail for these different types of what we call manipulation skills or tasks, such as getting the lid off of the jar. Yeah, so here's just a few videos of the robot using this technique to do all sorts of interesting tasks, like scooping pasta, getting the lid off the jar, opening drawers, and opening some boxes. And this is essentially a quick way, and because we use human guidance, to be able to build these motions very fast and gather data, when typically it would take months to be able to program the robot to be able to do this. Okay, so this is essentially where I think is around the 15-minute mark. I'm definitely happy to have questions since I know I've gone too quickly. Otherwise, I do have more videos I can show and so on, but I think it might be more interesting if people have questions about what they've seen.
I have a quick question on, you show this technique of when you show the robot how to do it. Is there a name for this technique?
Yeah, so this whole field is learning from demonstrations or programming by demonstration. So there's many different ways that you can show the robot how to do things, and that's the field that covers it. So that includes things like you can actually just use a camera and watch a person and then have the robot mimic. The specific thing where you physically pick up the arm and move it around is what we call kinesthetic teaching. So that's the particular technique. The reason why kinesthetic teaching is a little bit easier is that I don't have to figure out what you're doing and connect it to my motors. I just literally, you have moved my motors for me and I can just execute those motor commands. So.
And another question I have is like, how much of our research is robotics and how much is AI, or is it something different but complements, or is it how does that relationship works?
Yeah, so that's actually a really good question. And what people don't realize is that the field of AI started from robotics. So back maybe in the 60s, I don't remember the exact year, the Shaky the robot is one of the first robots that was ever built. And they wanted Shaky to essentially do something very simple, just cross the room with some obstacles in the way and get from point A to point B. And in this whole process, they realized that getting this intelligence to the robot is really difficult. And so it spawned this whole field of artificial intelligence where they said, okay, well, getting the hardware to work is hard. So why don't we take that away and just study the algorithms to just do the intelligence, and then later we can put those on the robot. So they kind of diverged in a path because hardware was just not ready back then. So 30, 40 years ago, trying to get any hardware system to be reliable was very difficult for AI purposes. And then now there's been definitely a concerted effort in the research community as well as in industry to connect those two things back together. Take all the machine learning things that Google and Amazon are doing and then put those back onto the robot. The unfortunate thing is that a lot of assumptions that you make without hardware go away. So you can't assume things like, I know exactly where the object is, because the real world is much noisier. So a lot of robotics AI research now is understanding how to get around those assumptions. And what does it mean that you have noisy information about the world, that the object is actually 5 centimeters to the right as opposed to where I thought it is? What does that mean now for my artificial intelligence algorithm?
So I actually know the answer to this already, but why did you decide to do a PhD?
Okay, good question. So I discovered that, so I started to get into robotics maybe my junior, senior year of college. So before then, I was a computer science major. I didn't really, and to be honest, I didn't really like computer science that much. I found it to be kind of boring because all it was some dots on the screen or some output of text. And so when I took my first robotics class junior year, we had a Roomba that you could program, and I got the Roomba to climb up a hill based off of an accelerometer reading, and that was the first time I was like, whoa, okay, I can actually program things to do useful things. And so because it was already my junior, senior year, I was like, uh-oh, I feel like I started off too late. And so then I applied to graduate school and discovered that research is just a lot of fun. So it's a lot of work, but it's fun for me because it's a question that no one actually knows if there's an answer to. And so it's not like classwork where the professor or the teacher says, okay, here's the answer, you got it wrong. And I'm sitting there being like, dang it, I got it wrong. It's more just like, no one knows how to solve this. And anything I try is interesting to understand. And then when you do actually get something to work, you feel a really big sense of accomplishment because it's something that no one has gotten to work before. And you're contributing some sort of knowledge to the world that didn't actually exist before, as opposed to being in class where it didn't matter if I got my test correct or wrong. Like, my answer isn't going to change whether or not that knowledge existed. So.
And then a follow-up question to that. So, most of the students here are, going to be an undergraduate. Maybe they're in their second or third years. If they are thinking about graduate school, what advice would you have to give them to help them decide whether or not that is something that they should do?
Also a good question. So grad school, so there's two things. If there's the master's program and then there's the PhD program. So in general, grad school in general now, I feel like, especially for STEM majors that want to do things like robotics that are not as well established, doing a master's is actually a pretty good idea because it really lets you get a level of knowledge deeper than your undergrad. So your undergrad is really about teaching you sort of a little bit of everything. And then if you actually want to be a manager or lead some particular expertise area, you kind of need to have more knowledge than that. So getting a master's lets you say, okay, well, I liked this one part of computer science. Now let me get some expertise in this particular area that lets me do something more than I would have been able to do before. It sort of exchanges maybe 3 to 4 years on the job for a degree. With that being said, there's the downside of the master's is that it's typically not something you have to pay to do your master's. So that's always something that I tell people to consider, is that if you're considering graduate school and getting a master's degree, just keep in mind that it's typically not cheap. But it could be worth your time if you really want to get into an area you basically, like me, didn't discover until too late, or you want to become a manager in that area, just be more of an expert in that area. For a PhD, this is a very different question. I usually tell people that if you want to make more money, and if you think that graduate school means that you have a bigger paycheck, do not go down the PhD route. In particular, because your salary coming out as a PhD is not that much higher than if you had a master's or an undergrad. And you have to take 5 to 6 years out of your life. So it means 5 to 6 years you do not make money. So it actually ends up being a huge hit in terms of financial reasons. So if you are thinking of a PhD for financial reasons, that is not a good reason. On the flip side, what people say about the PhD is that there will never be a point in your life where essentially you get to just do and study whatever the heck you want to do, right? I get to write a thesis and do research on this one particular area of robotics, not because a company is going to profit from it, just because it's interesting. And no other point in your life will you get to be able to do something like that without some sort of boss or manager saying, no, that no one will pay for that. You can't study that, right? Or you can't work on something like that. So yeah, I guess those are usually from a very high level how I think about the master's and PhD. In general, I'm always happy to give advice later if anyone wants to about more specifics. I've definitely done that for many, many different people that have considered graduate school if they wanted to do it.
How do you choose which school to apply to?
So this is where the master's and the PhD differs. So the master's, like I mentioned before, is not something typically they'll pay you to do. Typically, you have to pay for a master's. So what this means is that a master's and an undergrad are very similar in terms of financial outcome for the university. So they basically, when they accept you, they make money. So their master's students typically make money for the school, which means that you should definitely pick programs from a master's point of view that are your best bang for your buck, meaning that when you go out, people in your similar degree programs and universities get good jobs that make up for the money that you're putting in. So you definitely want to take those considerations, as well as you can always do the standard rankings, and that usually has a good correlation. But you can definitely find universities like, I will plug Georgia Tech's online master's program, where you essentially get a computer science master's degree for a fraction of the price because you do it through an online program, but when they give you your degree, it is the exact same degree as if you had done it in person and paid 2 to 3 times as much. So there are these kind of programs that exist that are just make more sense because at the end of the day, master's degrees make money for the university. For the PhD, this is really different. So PhDs, especially in STEM fields, you get paid to do your research. You'll get some stipend that is going to be barely enough for you to survive off of, but at least you can pay the bills and eat. What that means, though, is that you are very much dependent on some professor at some university having money at that point in time to fund you. Which means that even if you're the perfect student, have the perfect background, and the professor is the perfect fit, if they don't have money that year for you, they won't accept you. So when I tell people to apply for PhD programs, apply everywhere. And if you get into 2 or 3 programs, right, alone, the fact that they'll fly you out and essentially wine and dine you to convince you to go to their programs is going to make up for the extra fees that you paid for the extra universities you applied to. granted, this is very specific for engineering, like computer science degrees. This does not apply for the humanities or psychology or any of these others, because those kind of fields, there's a possibility that you actually have to pay to do the PhD. But in computer science especially, it's very, like, you are very well off as a PhD student in computer science.
Hello, Vivian, I have a question.
Yeah.
Can you hear me?
Yeah, I can hear you.
Will the robots have the capacity of self-learning? I think it will be a serious problem if it has ability to study by itself. Do you think it can be realized in the future?
No, I mean, that's a definitely, right? Skynet, are robots going to take over the world, sort of? Is that what you mean by your question?
I think robot will have the ability to study by itself. Now, many robots has a strong ability to collect and research or other ability set by programmers. They have no ability to study by itself. I think the robots have the ability to study by itself in the future.
Right. So definitely, so there's a whole field called reinforcement learning that is all about how robots can teach itself without a programmer at all. So basically, they have, it's very, what we call in psychology Pavlovian, where you say, if you do well, here's a prize. If you do poorly, negative reward, this is bad. And so they have come up with the field reinforcement learning that essentially lets the robot just wander and do whatever it wants. And if it did something good, it'll get a reward. And if it do something poorly, it gets something bad. And that actually can teach it to do things on its own without someone to program it. So that's definitely something in the future that robots will do. And so the way that I look at social robot learning and us teaching robots is sort of a stopgap in the middle. Just how you could learn things on your own without a teacher or a parent teaching you. It's just faster if someone helps you. So basically the way I see it is that if we can speed up the process, then maybe robots can become smarter in 20 or 30 years as opposed to maybe 50 or 60 years.
Oh, thank you.
Mm-hmm.
I am Yeung, and I am a student of my third year in my university, and my major is materials. Thank you for your presentation, and the Boston Dynamics released its new robot, and it's really a hot topic in China. And but I'm not a student of robots, so I'm curious about how difficult to make the difficult functions to come true, like the video show us.
Yeah, it's very hard. So this is why I showed the follow-up video of all the robots falling over, right? Specifically because, so as to give an example, right? So each of those robots that fell over, they're maybe $500,000 robots, so they're really not supposed to fall over, right? And each of these robots have a team of 20 to 30 graduate students programming them. And even then the robots will fall over. So it's very, very difficult to just get the robot to coordinate every joint to do things like that, which makes what Boston Dynamics is doing particularly impressive, because they have got essentially the controls part of how to move the leg in what motion well enough that the robot doesn't fall over, or can take into account like ice, and if it tries to fall, like if it starts to slip, it can even catch itself. So yeah, it's very impressive. It's very, very hard. And this is why, I don't know if you've heard, but Boston Dynamics has been bought and sold as a company so many times because they're doing really amazing things that people realize are amazing. But at the same time, we all commented how creepy those robots are. And so no one really wants to have a creepy robot around. And so these companies are buying them because they're doing cool things and then selling them again because they don't know what to do with them because no one actually wants to buy these robots. So.
Okay. Just to make sure, creepy means a little bit scary. So 有点奇怪、可怕的样子。That's what creepy.
Yeah.
Okay.
And I also have another question about I'm a student major in materials, and so I'd like to know if the materials is very important for the improvement of the robotics.
Yeah, no, that's a very good question. So there's a couple of areas where the materials is very important. One, just the weight. So you notice the robot dog video from Boston Dynamics. Now it's pretty quiet, but maybe 2 years ago it was really, really loud because they actually had a motor to be able to put gas into it and get the robot to move because it was so heavy. And so things like weight become really important because if the robot's too heavy, it needs a lot more power to be able to move. And if it needs more power and you have a battery, it might only move for 10 minutes. So then the material of the robot, if it becomes strong and light, become very important. You'll notice that the little flying helicopter, like drone sort of ones, that's another one where the lighter you get, the longer the planes can fly for, and becomes really important. Another thing where the material is really important, and actually is what I'm really interested in as well, is touch sensing. So robots don't have skin, right? So if I hit the robot on its arm, it would have no idea I touched it. And so there's been a lot of research in how to develop sensors and what materials can you embed those sensors in to put onto the robot arm so that when I touch the robot, it knows that I touched it. Or more importantly, if the robot bumps into a wall, into a table, into a person, it knows that it did that. Because right now, most robots have they can't tell that. So that, and it's also because those sensors just don't exist. They have to get small enough, light enough. They have to be able to integrate onto the robot. And what materials to do that, we still don't know. So it's definitely an open research question. So those are just the ones that come to mind. I'm sure there are many more other areas that could be useful for robots from a materials point of view.
Thank you very much.
And related to Yanxia's question, when you do your research, Vivian, do you collaborate with people outside of the direct field of robotics? And if so, what are sort of the interdisciplinary collaborations to make a robot actually work and not be too creepy?
Yeah, so in general, like this is why I said robotics and then all the different fields. Pretty much you have to work with the different fields. So if you're mechanical, you definitely need to work with some of the electrical and the controls with the aerospace. In my particular case, where I care about how people perceive the robot and how essentially do people think the robot is creepy, has a lot of collaboration with psychologists. And so really understanding so two things. One, just psychologists understand how we as people think. So maybe if we understand how we think, we can make robots think that way. And then the other side is just understanding what do people expect from machines and what do they expect when interacting with machines? And how do you make that interaction with the robot more what we expect so that they will use the robot exactly like how you intended. We do a lot of human robot interaction studies where we physically get people to come into our lab and play with the robot, teach the robot how to do things. And what you learn from these kind of things that psychologists know all the time is that people are really weird, and people do all sorts of things you don't expect. And these kind of understandings and collaborations with like psychologists and understanding human factors is super important, because if you don't understand these things, then you end up building robots like the Boston Dynamic ones that are cool, but no one knows what to do with and no one actually wants in their house. So.
So I have a question. I guess it's the mandatory question about robots and ethics, right? I mean, there's a lot of discussion and heat, especially in AI as well, and the world being crazy the way they are. Like, what are how is the industry protecting itself from not being in the future not being used on the wrong way, right? So how is there I'm sure there's a lot of talk about it, so just wondering from the inside, how is your perspective on it?
Yeah, so it's definitely one of these problems where, because robots are so stupid right now, most of us don't take this problem seriously, because I can't even get my robot to go down the hall without worrying that it's going to fall over or hit a wall. And so this is why, but that's the danger, is that because we know it's so stupid and we don't think about it. So we just build and program without thinking about the safety concerns when they can do these things. And this is what a lot of the senior artificial intelligence people in the field have started to realize. And that's where a lot of the news articles have come out, is that these people know that now, okay, we don't have to worry about that happening. But if we're not careful and start to plan ahead, 20, 30 years from now, what's going to happen when we have some algorithm that we programmed that didn't think about making sure it can't do something stupid have an effect? And so one of the things that has happened already, for instance, there was maybe 3 or 4 years ago when the stock market crashed unexpectedly because someone put an extra 2 zeros or 0 when selling a stock. And nowadays, stock is bought and sold using essentially AI, machine learning techniques that sell faster, buy and sell faster than we can press a button. And so what happened is that that person sold the wrong amount. This triggered everyone else's algorithm to sell and essentially tank the whole stock market. And what they had to do was essentially pause trading for that day and go back and revert. So these are the bigger worries of AI that a lot of the news are trying to capture. But of course, the interesting story is the robots are going to take over. But really, the main things about AI we have to worry about are just sort of these essentially these systems that we're using today already, that if you don't theoretically prove that something bad can happen, something in one day will trigger some particular edge case or some rare event that you would never have thought about while programming. So I guess in conclusion for that, there's a whole field now called provably safe AI, where they're actually throwing money into this research-wise to have theoretical proofs when you program or create your algorithm that nothing can actually happen outside of these particular parameters. And it's really, really important, and is a very theoretical field right now. But eventually, it's going to become bigger and bigger, especially when you start to think about how it's already being used in things like planes. So when the planes fly themselves, that's another case where those types of algorithms have already started to require theoretical proofs that the plane is not going to crash itself when 3 of these sensors break and this 4th sensor tells you this, right?
All right.
Hi, I'm Eden, and I have a question.
Hey, Eden, introduce yourself, please.
Oh, cool. So I'm friends with Yin, and I guess I'm a mentor now, and really excited to be involved.
She was our last guest speaker.
Oh, yes, I was the last speaker. My question is about sort of how do you see your career trajectory once you get your PhD? Are you going to go back into the for-profit world, or are you sticking with academia, or what do you think?
Right. This is a good question, one I've been getting very, very frequently now that I'm close to graduation. So robotics is a very interesting time right now because it's so popular. Universities are hiring a lot, which is pretty rare. Normally you'd have maybe 1 to 2 different openings. Now there are like 20 openings in a year. And then industry is trying to gobble up all the machine learning people, everyone who can work on Alexa and Google Home, people, and essentially also companies like Cynthia's company at like Softbank, where they actually do have these robots that are starting to get pushed out to the consumers. So in terms of opportunity, there's a lot of opportunity in all directions. For me personally, I've been straddling the decision of doing academia versus just doing my own startup for a pretty long time. But it wasn't until maybe 3 or 4 months ago that I kind of made a decision. So my PhD advisor and I are actually going off and doing a startup, trying to get robots into hospitals, and in particular try to get robots that can help nurses and physicians do a lot of the things such as moving things from point A to point B. Because we believe that some of the things that I showed here, the videos show that robots are at the point where they're, yes, very stupid, but they're still smart enough to do some of the very basic things to help out.
I'm working at a company called Butterfly Network, and we're building a portable ultrasound, and really interested in like telemedicine and things like that. So maybe we should talk offline.
Oh yeah, definitely. It'd be very, very good.
And Vivian, your advisor is also a woman, right? If I remember.
Yes, actually I'm really lucky. My master's advisor was a woman. My first PhD advisor is a woman. She switched universities halfway through my PhD, which actually happens more often than we realize. And then I got a co-advisor who's also female. So I have 3 female advisors in terms of my graduate degree.
All right, any more questions for Vivian? If not, then we'll let her go back to writing her thesis. Okay, thank you for your time, Vivian. We're gonna now bombard Cynthia with questions. So.
I don't think I need to answer any. Anyways, Vivian, go write your thesis.
Bye,
Okay.
Vivian.
Bye. Nice meeting everyone.
Okay, Cynthia, why don't you chat a little bit about your work at Softbank and Pepper and how you got into the field, because that wasn't what you studied exactly.
Nope. Vivian, why are you still online?
I'm figuring out how to leave. Bye.
Bye.
My work is not nearly as interesting as Vivian's. So in one of her earlier slides, you may have seen the Pepper robot. So Pepper is a 4-foot-tall humanoid robot. Let me see if I can actually find a photo of her. I'm going to just sort of put the link on the chat so you can see.
I can pull it up and share screens.
I'm just going to put it on the chat. So this is our robot. And the story of Softbank Robotics is also kind of an interesting one. Softbank Robotics actually came out of the acquisition of Aldebaran, which was a 10-year-old French robotics company. And so, this company had existed for a long time. until this really rich Japanese multi-billionaire called Masayoshi Son decided that this was a field that he wanted to enter. So Masa, ever since he was a little boy, was always interested in robotics, but, it wasn't really something that, he could sort of do himself. And he actually ended up going into telecommunications and sort of built this large sort of multinational company called Softbank Group, which is one of the largest telecommunications companies in Japan. Oh, you guys show a video?
Sorry.
Oh, no, you might as well show the video.
Meet Pepper, the irresistible brand ambassador that gives your Marcom teams a powerful new way to engage with consumers and gives your sales force a helping hand for those mundane tasks that might otherwise prevent them from building better relationships with their customers. Pepper is designed to be conversant and interact with customers in a natural, engaging way. Created with a unique combination of emotional intelligence and an array of sophisticated hardware, Pepper responds to touch, can listen, and even knows how a customer is feeling, which is why some of the world's largest and most innovative brands in the retail space have chosen Pepper as their brand ambassador, sales associate, and all-around engagement specialist. Westfield, one of North America's leading shopping centers, partnered with Softbank Robotics for the launch of Pepper's first retail experience in the U.S. The benefits to Westfield's customers were immediate.
Pepper helps that interaction with the concierge team by providing wayfinding, entertaining, and engaging our customers.
HMS Host is part of one of the world's largest providers of food and beverage services for U.S. airports. Pepper was chosen to be a host at their Pyramid Ale tap room within the Oakland International Airport, engaging with customers and offering food and drinks.
Okay, I have to stop right here and say that I was at the Oakland Airport and saw Pepper there in front of the restaurant.
Yeah, I mean, the rest of it, I don't know if it's really that interesting. It's basically just a really long commercial.
Right.
So you guys can watch it on your own time if you're really interested. But I think it's a good counterpoint in many ways to what Vivian's working on, because what Vivian is working on is what I would like to call sort of state-of-the-art, cutting-edge research problems. So she's really trying to sort of break new ground and solve problems that don't have a solution yet. With Pepper, we're actually kind of doing something a little bit different. We're trying to commercialize, i.e. make money from an existing product that works today. So, Pepper is our flagship robot. So it is our primary product. And, our problem is very different from Vivian's problem. So Vivian's problem is like, how can I build a robot that will solve, these problems for hospitals and nurses? Whereas in our case, we're really just trying to figure out how do we make money from our robot and, build a business around that. So with Pepper, like I mentioned earlier, it was really this sort of brainchild of Masayoshi Son, this sort of Japanese multi-billionaire. He made his money from telecommunications, and once he had, I guess, enough money, he decided that it was time to revisit his childhood dream and sort of wish fulfillment. I'm sure all of us have dreams from when we were younger, things that we would do when we were rich. Masa was rich enough to fulfill those dreams. So he actually ended up buying Aldebaran, which was this 10-year-old French robotics company, and then rebranded it as Softbank Robotics. So my job there is I lead product for our promoter solution, which is what you just saw the video for. It is a marketing solution. The idea is Pepper as a humanoid robot is very engaging. It is very novel, especially to people in America, and therefore it is a great way to attract attention and sort of help retail stores and banks and other sort of commercial businesses draw more people into their stores, as well as sell more things to those people once they are in the store. So, I guess sort of a couple of interesting things about that is that, the problem that we're really trying to solve is, how do we justify the price of Pepper? So Pepper is a fairly expensive robot. So, to what Vivian said before, a lot of the manufacturing robots are hundreds of thousands or millions of dollars even. Some of the consumer robots are maybe in the hundreds of dollars. Pepper is sort of a little bit in the middle. It's a $25,000 robot. So it's definitely more expensive than what, an individual person could afford, unless you were a very wealthy person. But it is actually a reasonable price for businesses. So a lot of Fortune 500 companies do actually come to us, asking to purchase Pepper because this is actually something that is affordable for them. It's not, a $100,000 or $1 million investment. It's a $25,000 investment, which is actually fairly reasonable for a robot of this sort of complexity. So not really sure what else you want to hear, but I am more than happy to talk about Pepper and the business and what it means to sort of commercialize a robot.
Oh, so I have a question. I'm a product manager, and you said that you're leading the development of sort of like the product road. Does that include like the roadmap stuff? How do you sort of figure out what sort of like feedback and signals are you using to develop the roadmap for the future of Pepper?
A lot of user research. So we do different kinds of user research. So one of the forms of research we do is, purely observational. We have Pepper in a number of different public environments at this point. So, we observe how people interact with Pepper. So when and these people are sort of end users, right? So these aren't our customers. These are not the people who are purchasing Pepper. These are the people who are just, walking by, interacting with Pepper. So we do a lot of those types of user studies. Separately, and this is sort of something that you don't actually really see, and sometimes you may not even think about, is how do our customers interact and program Pepper? So previously, when the first version of Pepper came out, the only way you could get Pepper to do anything was, if you used, our API SDK and, coded in Python, essentially. And that was the only way to get Pepper to do anything. If you wanted Pepper to raise its arm, that's what you had to do. And it was very, very difficult for some of our early customers to get started because a lot of them did not have engineering teams, who could program Pepper to do the things that they wanted. So one of the things that we actually had to do to, sort of help commercialize Pepper was create this sort of really simple web interface that non-technical people could use to, get Pepper to speak or move or, display imagery on its tablet or, have clickable buttons and sort of things like that. So there's a sort of whole separate area of research that we also do there around our customers. And then a lot of it, honestly is just sort of testing different things. So we do a lot of A/B testing to actually see what works. And that's sort of more small scale testing. So we'll try it out maybe with a handful of customers, see what the reaction looks like, see what their feedback looks like, see what their customers' feedback looks like, and then have that feed into our loop. So we use a sort of a development process called, Agile Scrum. Basically consists of about 3-week sprints. And that lets us sort of, respond to market feedback relatively quickly. And then we'll adjust accordingly. So that's on the software side. The hardware side, hardware is hard. Hardware has much longer cycles. So it's actually pretty challenging sometimes to align our sort of software and hardware roadmaps because, software sometimes will be like, hey, hardware guys, we really need a better microphone in here. Pepper can't hear in loud environments and doesn't know what's going on. And there's really only so many things that we can do on the software side. And then hardware will come back to us and be like, okay, we'll get back to you in 9 months. So I don't know if any of you are hardware engineers, but that's sort of a constant source of constant source of friction.
Dalton raised his hand. I like, that's my everyday life.
Yeah, hardware and software. But yeah, no, I guess I don't know if that answers your question, Eden. But that's what we try to do with roadmaps. It's difficult. I think also because our customer base is so wide and varied that sometimes one of our challenges also is just trying to understand which customers to listen to. So, we have some customers that are, really like from the marketing team, and, they're really concerned about ROI and brand and things like that. And then some of our customers are really just kind of more engineering hacker types, and they just want to build something cool. Like they don't care really, whether Pepper, actually helps them increase sales at the end. And our challenge is, actually trying to make sure that we choose the right customers, which is an interesting concept, knowing which customers to fire, because sometimes you do want to fire your customers, is an interesting sort of, I guess, skill. And this is sort of where, if you do get into product management, things like personas and all of that come into play.
Cool. Thank you so much.
Actually, Eden, are you working? I mean, how is life right now as a product manager, since we do have you here? And because you also are working on a hardware product, right? But I'm sure there's a software component.
Yeah, so I'm a product manager at a company called Butterfly Network, and we're developing a portable ultrasound probe. So feel free to check us out, butterflynetwork.com. And basically, it's a ultrasound probe that you plug into your iPhone, and it has a software interface through our cloud storage where you can capture photos, upload them to the cloud, and I'm leading the development of our software product. But there's all sorts of applications with telemedicine that we're looking to get into, and definitely trying to make it easier for people to be using a technology like ultrasound. So I spend a lot of my days sort of thinking about how to become a better product manager and how to think more broadly about product strategy. So it's super cool to hear other people talking about this stuff.
Do you guys also use Agile?
We sort of use a modified form of it. I think a lot of us have come from different companies where sometimes it works, sometimes it doesn't, but definitely having, predefined goals of what features do we want to build and get into a release that's going out, this month or next month. And that sort of helps to inform the roadmap and stuff.
Yeah, I'm asking because I'm Agile coach, Scrum Master myself, so it's great to hear that.
Very cool.
There's words here and there.
Cynthia, how did you end up working at Softbank Robotics? Because that's not what you studied. Back to that comment.
Yeah. So in undergrad, I went to Penn. So I went to the same university as Yeung. I was in a different program. So Yeung was in the Cool Kids program, which is Huntsman. So it's where the cool kids were. And so Yeung did the international. It was international studies. What did you guys call it?
Yeah,
international studies.
We learned languages in which we can communicate with people instead of learning languages with which to communicate with machines.
Yeah, so I was in the M&T program, which was the engineering and business and learning program. So we were the super dorky kids. So I was I did that. So I did engineering, systems engineering, and on the Warren side, I did legal studies, marketing, and management. And actually, my first job out of college was actually at a credit card company, funnily enough. I was working for a company called Capital One, where I was on the discontinuous innovations team. And we were trying to, this was a really long time ago, I'm dating myself. This was when we were trying to get RFID chips into credit cards because nobody had done it before. So, we were really trying to sort of bring the fintech game up at Capital One. I left that company after about a year to join Google, where I was there for 5 years. working primarily on the maps project. So Street View, aerial imagery, some of the early Google X initiatives. And after about 5 years, I got a little bit restless, wanted to do tech for good, and ended up on a ship for a social entrepreneurship accelerator program, where we were on this ship traveling through Southeast Asia with the Archbishop Desmond Tutu, as well as people like Megan Smith, who was actually the former CTO at the White House before Trump came to power, and had a really great time there, but learned that social entrepreneurship was not really a great fit for me. But I still wanted to do startups, so I ended up at a travel tech startup because I liked to travel and thought that that would be a really great idea. Did that. We got acquired earlier, but I guess it was like a year or two ago now. And then at that point, I was like, okay, what do I want to do? So I've been working in tech my entire life. I like tech. I like startups. I have a pretty good idea of what I don't want to do anymore. And at the same time, what was happening was that I'd also been editing Vivian's research papers ever since she started graduate school. Basically, so Vivian is a great researcher. She is not necessarily the best writer. So as you may have heard during today's talk, she sometimes forgets to spell out acronyms. And this happens in her papers too. So she will use all these acronyms in her paper, and she completely forgets that she actually has to at least describe the acronym once so that everyone else knows what she's talking about. So those were the things that I kind of did for her. And over the course of a number of years, I realized I actually knew a lot more about robots than the average person. So I started looking at robotics, and one of the things that Vivian and I are both interested in working on long term is actually elder care robotics. So both of us think that that is a really important problem. I think part of it might be not to stereotype too much, but because we are Chinese and there's this sort of whole deference to elders and filial obedience, and sort of those types of concepts are very ingrained in our nature in some ways. I think this is sort of something that we both think is a sort of worthwhile problem to be working on. And it, again, is sort of very satisfying because it is tangible and impacts the real world in a way that, pixels on a screen don't necessarily do.
How long have you been at Softbank now?
Ooh, just over a year now.
Okay.
So a year and a couple months, I think, at this point.
And
it feels like a much longer time than that, though.
Yeah. And do you see Pepper potentially being used in elderly care going forward?
Yes and no. So I think Vivian earlier had talked about, different aspects of robotics. And, where I would say Pepper falls into that category is really around this idea of social robotics. So again, Pepper is designed very much with, principles of like a human-robot interaction in mind. It's, it's supposed to be a social robot. It's something that's supposed to engage you. However, what Pepper does not do is manipulate. So although Pepper has hands and, although it can move and navigate, Pepper's hands actually, it can't hold on to anything. They are purely for expressive purposes, which limits its usefulness in certain kind of elder care settings. So, things that Pepper could be useful for and, actually have been used for in Japan, for example, would be to give medical information. So, you could hypothetically, ask, a Pepper that was designed for a medical setting, like, I don't know, what kind of medication should I be taking or things like that. And, Pepper could scan a database and give you answers there. But, Pepper wouldn't be able to, actually give you the pill, for example, because that is not the way that it was designed. So there are certain use cases where Pepper could be very useful. But, for the type of work that Vivian and I want to be doing long term, Pepper would not be the right robot for that. manipulation is not a solved problem. It is a very difficult problem.
Hello, Kathy. I will have a question. Do you think paper is competitive for the online business? Because we also can use phone to do what we to for a customer. We also can use phone to do this.
Yeah. So what we like to say actually is that Pepper plays well with all sorts of devices. So we don't recommend that a customer complete their entire customer journey on Pepper. What we typically actually recommend our customers to do is to have Pepper start the interaction, have Pepper basically be the point of entry, and then push their customer, so the end user, off to a different channel. So maybe it's about continuing the rest of their customer journey on their phone. Maybe it's pushing them to a human sales associate even. There's a lot of ways that Pepper can work with other devices, basically using the IoT Internet of Things concept. So for example, there's a sushi chain in Japan called Hama Sushi, and what they do with Pepper is it's a very, very basic use case, but they have Pepper attract people to the sushi store, and then Pepper will actually communicate with a different device, which is essentially a printer of sorts, that will then print out a sort of queue slip. So you are number 3 in line. And that's actually how that particular sushi shop uses Pepper. So you're absolutely correct. A lot of the functions that Pepper could perform, you can do on a website pretty easily, actually, in many cases. But what we found is that even when the specific action can be done online, a lot of times people still prefer to interact with Pepper anyway because it's more fun. Much in the same way that if you have, trying to think what's a good example here, you could buy things online, and I buy a lot of things online too, but sometimes you just want to go into a store and ask a couple of questions of someone before you actually make that final purchase. So that's what a lot of our customers think when they purchase a Pepper for their own businesses. And then a lot of them are actually also thinking about how to enhance their customer experience too. So an interesting example of this would be companies like Warby Parker, which is this sort of hipster glasses shop that really started online. So Warby Parker originally was entirely an online business. They didn't have any stores. Everything was online. All of their customers came in through e-commerce, and they were doing really well. However, what you've actually seen in recent years is that Warby Parker has started to open physical stores. So even though they had this great online business and a lot of people were buying the glasses online, they found that it was still important for the growth of their business to start opening physical, stores, where people could actually interact with their products.
Thank you.
Hi, I have some a question that as we know, it's very expensive for us to afford a robot. So it's impossible to cut down the cost to that in the future people can afford it to have a robot in our own home.
Yeah, no, it is. You're correct. It is very expensive. And this is actually, one of the reasons why, for Vivian's business, they're starting off with hospitals, because today, at least, given the cost of the technology, really hospitals are the only, ones that could actually afford, the kind of robot that Vivian and her professor are working on. The idea would be, initially, their initial market would be hospitals, and then, once the technology's gotten cheaper, then they could start moving into elder care homes, and then eventually, many years from now, the technology would become cheap enough that they could actually, make it available to individual consumers like you and me. So that's sort of just sort of part of the technology life cycle, is that, very often the earliest forms of, any technology are usually too expensive for, normal people like you and me. And, really only kind of large businesses or large institutions can afford them. Much in the same way, if you think about the first computers, right? So, the first computers, like the IBM mainframes, these were these massive, massive computers that, took up the space of an entire room. And there's no way that, any normal family could have an IBM mainframe in their home. Like, that just wouldn't make sense at all. And yet, here we are today with, computers, phones are really computers in many ways, that everybody has. And, it hasn't really been that long when you think about it. So absolutely, a robot like this today wouldn't make sense for, a family to own. But it's not inconceivable that, 30, 40 years from now, the technology will become cheap enough that you could actually make it affordable. And, actually in China has been doing a really great job with this, in terms of affordability. A lot of the costs are just, things like sensors and arms. Arms are really expensive. So to the extent that you cut down on a lot of those components, you actually can drive the cost way down. So for example, Pepper is really expensive because it has, many degrees of freedom, and it can also move, and the sensors are like really advanced, and it's really beautifully made. So if you look at the actual craftsmanship on the robot, there aren't any pinch points, meaning that even if you put your finger where the joints are, your fingers would be fine. The robot can move, you wouldn't hurt yourself. So it's a very sort of well-designed robot in that way. But, you could easily imagine a situation where, you remove all the arms on the robot, you remove the waist. So, we have a waist on Pepper because it's a Japanese robot, it has to bow. But, there's no reason really why the robot has to have a waist otherwise, unless you needed it to do that bowing movement. So, there's another couple $1,000s right there. And then, of course, there's the profit margin as well that's built in on top of that. But, you could absolutely make a robot very similar to Pepper for a fraction of the cost. And to be perfectly honest, there are Chinese companies that have done that already. So they share our same factory, and without going into, IP, intellectual property lawsuits and whatnot, so China is definitely at the forefront of making robots cheaper.
And thank you.
Okay, I think we're right on time. So any additional comments or questions for or from Cynthia? Okay, well, thanks for making the time, Cynthia. And Andre, thanks for setting up the call. And thanks for everyone for attending. Dalton, good luck in your interviews. Not good luck for you, good luck in general. And hope you speak to some good candidates and let us know.
I did take meeting minutes, so I'll send those to you, and I just have to find the right format.
Okay, send it over. Thank you.
Thanks, guys.
Thanks,
Bye.
All right, have a good rest of your day and evening, all.